Okay, got it.
Good morning all, and welcome to another lecture in geomorphology. This class is part of the international set of lectures between UMS in Indonesia and Kobe University in Japan. And today we have a guest lecturer who's going to talk to us about planetary geomorphology. And Balazs Bradak, who's the guest lecturer, is going to introduce us to geomorphology outside the Earth. He's a specialist of interplanetary research, and he has done some recent work on extraterrestrial oceanography. He's also famous in the world for his work on the AMS methods on sediments. You might have heard him talk at different conferences. He has done a lot of quite controversial and new papers using this method and on the topic. So if you have also any question on that, you can also ask him. But today we are here to listen to him tell us more about basically our planet by trying to understand what's also out there. What is special on Earth and what is not so special on Earth is something that we might wonder as well. And knowing what's happening on other planets is also helping us understanding what we have on our own. So Balazs Bradak, Dr. Bradak, the floor is yours. Thank you for coming today to the lecture. And
thank you. Thank you for the invitation. Thank you so much. And the nice words. So let's start it. Okay, it's a long travel. We will travel through the solar system. And as the title said, it's planetary geomorphology. And I was thinking a lot that how should I build up this entire presentation, because planetary geomorphology is quite a big topic now, thanks to a lot of different satellites going around various planets and spreading out from the solar system. So I decided that I would like to give you some basic knowledge about the solar system and the formation of the solar system, because it helps to understand why the different planetary bodies includes the planets and the moons of the planet, asteroids, and everything what you can find in the solar system and beyond the solar system. And then we will take a field trip in the solar system from Mercury toward the edge of the solar system. We will pass even Pluto, and then we leave the heliosphere. So we leave this bubble around the sun, and we will go to the interplanetary space and looking for exoplanets, which are not in our solar system, and check that is there any possibility to do some research there. The main topic which connects this field trip is the volcanism. I chose volcanism because it's an interesting and most likely very entertaining topic, and it's interesting because it's so versatile in the solar system that it's worth to talk about it and worth to visit other planets to do some research on volcanism. So it's through we are traveling beyond the pale blue dot. The pale blue dot is nothing else but the Earth, and you can find it in this figure. This photo was taken, as this image was taken by Voyager 1, and here is Earth, this pale little dust-like dot, and in this vast big space, and this vast big space is kind of nothing else than our solar system and beyond. But let's first talk a little bit about the formation of the solar system. And our solar system, when I use solar system, I talk about our solar system, but this formation, the way of formation can be applied or mostly any solar system around the universe, based on our recent knowledge. It's important to tell that, but based on our recent knowledge, it can change by time when we have more and more knowledge about the universe. Generally, the basic of any solar system is a dense cloud of interstellar gas and dust. This is the very beginning. it's in the interstellar space. It's really nothing else, just the mixture of various elements and dust, which suddenly changing their shape and form. This cloud is hit by some shock wave, some gravity wave goes through on the universe, for example, triggered by an exploding star, a supernova, some star reaching the supernova phase, and this explosion goes through the universe, hitting this dense cloud building by gas and dust. Or it's not necessarily, we don't really necessarily need a supernova, but for example, a passing star can change the gravity around it, and this passing star triggers the collapse of this cloud. And when this cloud collapses, it creates a solar nebula. And this is a spinning, swirling disk of material, which called protoplanetary disk. And this is generally the first stage of in the evolution or a life of a solar system. Okay, it looks like this. These are different protoplanetary disks around, let's say, around our solar system. And you can say that there is a center. There are some gas and dust and different elements build disk around this shiny center. But what is the protoplanetary disk? So generally, the center at the center of the protoplanetary disk, the gravity pulls more and more material in, and this more and more dense material, it increases the pressure in the core, which leads to the fusion of hydrogen helium. And this is the moment when this fusion happens, the sun, or any star, starts to shine. That's when in this moment the sun is very, very young. It's partly the sun what you can experience now, but it's this fusion starts, and the sun, the core of our system is ready to develop. Further out of the disk, this disk is moving around and around and around, and in the different paths of different size of grains and materials, this dust and coarser grain material start to clump together and create a so-called planetesimals, which later forms the protoplanets. And this protoplanet has bigger and bigger gravity, and it kind of starts to collect everything in his path and just growing and growing. So larger and larger objects are forming. Sorry, I try to put this somewhere. Larger and larger, okay, no, sorry, are forming. And there are different possibilities what can happen with this object. Some of them grows big enough that the gravity of this mass can form a sphere, sorry. And this sphere will be the core of planets, dwarf planets and larger moons in any solar system or our solar system. Of course, there are smaller pieces, and they don't really form any spheres, and they became the asteroids, like in our asteroid belt, the main asteroid belt, and in our solar system. And there are leftovers. The leftovers are the asteroids, comets, meteoroids, and some different irregular moons. For example, at the edge of this protoplanetary disk, in our case, it's an Oort cloud. So this is generally how planets or planetary bodies and their satellites. In our case, when I say satellites, in the case of different planets, I'm talking about moons. Okay, just in our case, the moon is always our moon, Luna. So it can be a little bit confusing at the beginning. And what happens after? That's the question. So we have planetesimals and protoplanets. And let's see what's going on with what's going on with the planets. First, as I mentioned, this planetesimals form. They get together. The name the planetesimals indicates that these objects are relatively small. So it's several meters to hundreds of kilometers big. This is the way of, or first step of creation of a planet. There are protoplanets, which is the next step, and they are size of a moon or bigger, and they goes to the size of a dwarf planet, and the interesting thing that this kind of protoplanets already has geology and geomorphology as well. Sorry if I talk about geology and geomorphology in planetary science. Generally, it's surface geology or geomorphology. It's definitely in some sense same and overlapping science topics. Okay, so for example, Vesta, which can be considered as a planetesimal of a protoplanet, has its own geology. So they created already different formations based on the geomorphological features of it and the suspected age of surface. But we can get further from protoplanets, because in a protoplanet history, the accretion plays a sorry, I try to make it disappear. Okay. So in the protoplanet history, the accretion plays a very, very, very important role, and we will see now why. So the material accretion is when the planets are getting bigger and bigger, picking up more and more material in their paths when they're moving around the sun. During this accretion, it means impacts. And during this accretion or impact, the surface and below the surface, the material is melting. And also, it means increasing mass. And it means that the gravity became a significant force. So we have heating and we have gravity as well, which results that this melt or heated melt substance, in this heated melt substance, the lighter and heavier parts are separated. Okay, so the heavier substances is going down, and they will create the core or the mantle. The most likely the core of the heaviest one is the core. Elements create the core of the planet, and the lighter one is kind of floating on this on the heavier substance. So this generally led to a internal differentiation of some object or the planetary object, if they have enough gravity or if they have enough heat. Or together, it's an important combination in the life of a planet. So there are some, of course, there are some, in the case of insufficient gravity, there are no, this separation is internal segregation of the material is not happening. And generally, it gets some undifferentiated small moons like that. There is another situation when, for example, the source material, which gets together during the accretion, it's very homogenic. So there are no differences. That's also led homogenic inner structure of the planet. But very interesting, Vesta, what we just talked about, Vesta Vesta is not a big object. You can see the size relatively. So it seems that Vesta has inner, even Vesta has inner structure. But of course, in the case of the planets which we will visit, and even moons or satellites, what we will visit, they have planetary differentiation. And it's an interesting thing if you see this figure that our planet in the solar system has very versatile inner structure. So even if you have the heat and if you have a gravity, there are some additional components, parameter which we have to consider. Why Mercury has this giant core, and why, for example, the gas giants or the ice giants has very different structure. This different inner structure, of course, will influence the volcanism, which we will talk about a little bit later. Why these things happening? It's generally, if we want to understand why the different planets has different chemical composition and different inner structure, or different chemical composition of the inner structure, we should kind of go back to our chemistry class and the periodic table, and to the Goldschmidt classification, which is kind of geochemical classification of the elements, and it shows that how different elements would behave in the case of the planetary formation. There are, for example, siderophile elements, which are most likely mixing with iron, and they are concentrated in the planetary cores. Okay, so they most likely create the core of different planets. And there are lithophile elements which are, of course, going to the most likely in the surface materials, and you cannot really find them in a cores. There are, of course, other groups, the calcophile and the athenophile elements, which have different role in the case of Earth. But let's not talk about the calcophile elements in this moment, but let's talk with the athenophile elements. That these are the gases and volatiles. And in the case of Earth, in bigger mass, you can find them in the atmosphere. But these elements plays key role in some other satellites' body. So like other satellites, let's say lithosphere or lithosphere-like ice crust, will contain these elements, which generally in the Earth can be found in the atmosphere in bigger amount. So why is it? Why this is happening? It's easy to understand because generally that distribution of the elements is defined by the distance from the sun. It's just simply because of the temperature of the sun, and like in metals and silicates, rocky materials most likely can be found in bigger concentration in the terrestrial type planets, like let's say Mercury, Earth, Venus, Mars. Different type of materials can be found in the gas giants like Jupiter and Saturn, and around those planets, their satellites has already mixture of silicate and, let's say, water ice, and it just go in a different ice direction. Like, for example, ammonia ice you can find in bigger amount in further and further from the sun. So the volatiles became one of the main components of the for example, the surface of those planetary bodies. And now you can imagine the situation, and our field trip will really examine this feature, that what's happening when we know what's happening in Earth with the volcanism. we know what we can expect something about the terrestrial planets. The terrestrial planets, like how I said, Mercury, Venus, Earth, and Mars. But what's happening? How volcanism can happen in different satellites with ice? So that's an interesting question. Is there anything like volcanism? Yes, there is, and this is one of the most interesting part of the let's say interplanetary volcanism field trip, what we will just go on. Okay, so let's our voyage begin. This is the kind of figure of Voyager 1. Voyager 1 is the one of my favorite spacecraft. It's now it's out of the heliosphere. It's out of our solar system. Not really working well in this moment, by the way. But this was the spacecraft which took the photo at the first slide of this presentation, the pale blue dot photo, for with the Earth like a dust. So let's. We cannot really sit on that satellite, but imagine that we're traveling together with Voyager 1, and then let's see that how the volcanism is happening on different planetary bodies. Okay, so first the Earth. Okay, that's our starting point. What do we need for volcanism on Earth? What is the recipe of terrestrial volcanism? And if we see the ingredients, what do we need? We need a planet with differentiated internal structure. That's for sure we have. It's good if we have internal heating, which in the case of Earth, it's come from radioactivity, radioactive decay of radioactive decay of radioactive elements. It's kind of a heat. We have a giant nuclear power plant inside our Earth, which provides enough heat. And you believe or not, but we have a little residual heat still from the early planetary stage. It comes from the enormous amount of meteorite impacts hitting the Earth and melt the entire surface. This little heat is still there. And we have, of course, convective flows and plumes triggered by this heat, and these plumes and convective flows surfacing or subsurfacing and creating volcanism in our surface. Very simply put. Okay, it's of course we are not focusing fully in the Earth now, and it would be another lecture if I explain all of the possibilities and things related to volcanism, but these are like a recipe. These are what we need. Let's keep it in mind. What are the spices? How can we add more and more flavor to our volcanism, and how can we make the terrestrial volcanism so versatile? Like if we have global tectonism, plate tectonism, now that makes the volcanism so versatile. No, if we have the Middle Oceanic ridge, which has some type of volcanism with certain type of volcanic material and a certain type of magma, or we have subduction with a totally different character of volcanism, or even some intraplate volcanism, like how I wrote a pinch of rift volcanism, a teaspoon of plateau basalt, and a slice of subduction. We have very versatile volcanism on Earth with very different character, and it's a good start to rely on when we go to other terrestrial planets and try to discover the morphological features of volcanism, because we can look for shield volcanism, we can look for stratovolcanoes, we can look for volcanic cones, we can look for a spread of tephra around the wasteland. So we know what we are looking for in other planets, or do we really? And this is the question of the planetary geomorphology. Okay, so let's before it begins, we have to know about one more component which really influences the volcanism, not on Earth, but on other planetary bodies, and this is the tidal force. So imagine the situation. In our case, the moon influences our oceans, and we got this rhythmical tidal process. But imagine the situation if you are a small moon, like let's say Europa or Io, moving around and around a giant planet like Jupiter. This tidal force is much stronger and bigger than in the case of the Earth and Mars. I will not go deep the physics of tidal heating or tidal force. You can find a lot of information online if you look for it. It's just an idea, or just the fact that imagine this giant mass, how it can kind of distort or deform the entire planetary body, in the case, for example, of Jupiter or Saturn. And it reaches some level that it causes some heating inside the satellites. Okay, it's some kind of frictional force altogether with the moving of the mass. So this tidal heating, even if you don't have radioactive material or the leftover of the very early stage of planetary evolution, the heat from this early stage, you have some heating inside, and this heating will be a key for some planetary bodies and some volcanism in planetary bodies, because this tidal heating can create very similar, theoretically very similar effect, like in the case of Earth, the convective flows or plumes. Okay, so please keep it in mind. And when I say that, here comes the tidal heating, or the tidal forces as heating mechanism, then you just imagine that giant planet and its gravitational influence on this small satellite. Okay, let's go first. Mercury. The Mercury is an interesting situation, or Mercury, the volcanism on Mercury, it was a big question for scientists for long, because of the surface of Mercury. Mercury contains a lot of craters, and when some planetary body or planet contains a lot of craters, like the moon, it indicates that the surface is old. You can imagine if the surface is renewing, those craters are disappearing. But in the case of Mercury, it's heavily cratered. So it may indicate that there is no surface renewal, but there are some ancient plains or plain-looking geomorphological features which question this geologically dead state, because there has been two theories. One said that there are some erupting volcanoes which filled this surface, these plains, with lava, and this definitely volcanism, and this comes from internal heat, like in the case of Earth. They most likely, Mercury is a terrestrial planet after all, although it has a giant core, but it can have heat. Or another theory was that these plains were formed by impacts, and when an asteroid impact to the surface melts, and that melt can fill the cratering. Now, after all, it seems that when the messenger spacecraft reached the surface, and they got relatively good resolution, in the sense of planetary science, good resolution pictures, and they recognized some volcanism like shield volcanism-like features. This, for example, this one. They believe it's something like a shield volcano. They try to compare it to the Hawaiian Islands, like it's some kind of hotspot volcanism, or the Olympus Mons on Mars. It's come from. They believed or thought that it's connected to convective plum, so the hotspot volcanism. But it seems that it's a little bit different in the sense that it got a crater filling volcanic style. That it's kind of unique because there is only one other planet where you can find it this kind of things common. It's a moon. It's not a Mars or not an Earth. Mars and Earth has very lot of similarity. We will see. A moon seems to have very similar volcanism compared to Mercury. You can see the crater, and in the crater there are some lava floor shield volcano type of crater filling volcanic material. So this is Mercury. After all, it seems that maybe Mercury is geologically dead now, but it was not fully dead. There was some volcanism on this planetary body. If you're interested in more information here, I try to add a lot of references you can find on the different sheets. Okay. Now let's go to Venus. Venus was a difficult planet. Venus is very shy, in the sense of Venus has very thick atmosphere. And this thick atmosphere is prevented the observation of the surface. There are some lander, like Venera. It's a Russian. There was a series of Russian lander. They landed on the surface of Venus, but Venus atmosphere is carbon dioxide and some kind of sulfuric acid. Plus the heat. It killed these instruments very, very fast, but the surface looks like this, by the way. So it's a real, a color is not real, it's colored, but the surface looks like this. But how can we see the surface now? It's thanks to other satellites, which with some radar system, they scanned the surface of Venus and discovered a lot of interesting and very, very versatile forms, which I will introduce you some not even clearly known, or how can I say? There are theories that they are volcanic or subvolcanic origin, but not exactly 100% what we know about it. There are the nova or novas. These features. So you can see some concentric fault system goes around some diapir or some subvolcanic body. On the surface of Earth, very similar fault system can develop, for example, evaporitic diapirs, so salt diapirs during various tectonic processes. So this can be some parallel thinking, comparing those diapirs to the Venus nova concentric fault system. So this is subvolcanic body. The surface geomorphological marks of a diapir below the surface. So now that here comes the corona. Coronas are also big questions. These three are the big questions. I mean, most likely these two. Their origin and their formation. So that corona's formation, it's volcanotectonic, tectonomagmatic structure, which has this concentric ridge, which may be associated with lava flows, or not, or some volcanic dome formation, and this concentric features are really like a shield volcano. This different chronologically different effusive products we don't know in this moment. And the arachnoids, they got their name from this web, spider web like structure. Arachnoids are referring to spiders, and maybe similar to the formation of nova, plus some compressional extensional stress field, what they showed, but their formation is still under debate. Of course, when more and more information we have, more and more questions we have. So there are a lot of theories about the arachnoid formation of arachnoids. But one of the formation is similar to nova, is subvolcanic body or bodies. The surface appearance or surface indication of some subvolcanic process. But there are mostly volcano like features. No, they more like some kind of shield volcano / cone. The size from 30, that one is around 30 kilometer diameter. It can grow bigger to 300 kilometer, and so even it can contain smaller volcanoes here, like parasite cones or parasite volcanoes. This radial bright or dark or grayish in the photo radial features are lava flows or suspected lava flows. Okay, and there are calderas as well, indicated by the white arrows, and together with some concentric features, most likely like some kind of concentric lava flows or some material related to eruptions. There are personally I like the shield volcanoes or these shield or steep-sided domes. I think they are beautiful. You can see here the group of shield clusters. They are not so big, but it's like a shield volcanoes doing some party on the surface of Venus, and these are just simple beauty. Who knows that generally Venus, some kind of plate tectonism is suspected on Venus, not definitely like our global plate tectonism, but like an ancient Earth, very ancient early Earth plate tectonism is suspected on Venus. Who knows that this chain of steep-sided domes are not related to some moving plate over a plumb. So this is, oh sorry. So this is although Venus has a thick atmosphere, like I said, the Magellan spacecraft has a radar system, and they were able to kind of mapping of to map the surface of Venus, and this is one of the geomorphological map consists the information about different volcanic or tectonovolcanic features. So if you're interested in Venus, there are and you are a volcanologist, you can be planetary volcanologist in the surface of Venus. There is a lot of things to discover still, of course, and there will be there. Mars is our next step. So we are just arriving to some important the point of our field trip, because Mars is the last terrestrial planet in our solar system, and this is the moment when we arrive to some planet which is our next target as a human space a part of a human space discovery, and maybe terraforming, but these are science fiction in this moment. But we know a lot about Mars, even without going there. We know a lot thanks to massive amount of satellites and the different kind of spacecrafts continuously arriving to Mars. We know that much about the surface or the surface development of geomorphological history of Mars, that even we can have a chronological description about the development and formation of different type of volcanoes on the surface of Mars. I think it's amazing. It's generally we can describe the geomorphological and geological history, volcano geomorphological history of Mars. It thanks to very basic things, and I already told you about this, or not told, but mentioned that in planetary bodies the amount of craters are very, very helpful to decide the age of the surface. And based on this crater counting method, they were able to, and some other geomorphological observation, like for example, the distribution of lava flows and different kind of geomorphological feature, they were able to reconstruct the geological how can I say, volcanic history, or main volcanic history or the history of volcanism on Mars. Generally, these are the different regions where the key volcanoes are: the Tarsis, the Elysium, Syrtis Major, and the Hellas region. And seeing the age of or different periods of the history of Mars, maybe the most stable is the Tarsis. So you can find the Olympus Mons here. I will not talk about Olympus Mons. I try to avoid to talk about Olympus Mons because Olympus Mons is the biggest in the solar system, and everybody always mention it. If you want to read about Olympus Mons, please, you will find the based information, based amount of information on internet or any scientific site. But so the important thing is that they could reconstruct the volcanic history on Mars from the Noachian, let's say, which is the start of the activity. The pre-Noachian age is a big question mark now. That's what happened with the Mars. There are even theories which says that the planet was not even in the inner solar system. It arrives later, but in the Noachian. But these are theories, okay? And that this is the period when generally Mars got the pre-Noachian, when the Mars got this dichotomy, these differences between the southern highland and the northern lowland. Okay, the pre-Noachian followed by the Noachian period is mostly basaltic volcanism is the characteristic volcanism, which means that it's effusive. So you cannot really find giant volcanic eruptions and super volcanoes putting significant amount of material in the early atmosphere of Mars. You most likely find sheared volcanoes and lava plains, but there are some pyroclastic flows. So don't be fooled my words. There are pyroclastic activity as well, so explosive volcanism, and explosive volcanism, but most likely effusive volcanism was the key. Following by Hesperian and Amazonian, which periods the volcanism gets more versatile, and here comes some example about the volcanism on Mars. the explosive volcanism or has been a question, by the way, on the case of Mars. Were there explosive volcanism or not? It seems that there were it's called, the formation itself is called Medusa Fossa formation, which I try to not to cover, and some research targeted this area to find the results of this is explosive volcanism, and it seems that the other part is Hesperian, but since the Amazonian, this formation went through some reformation, which is characterized by the distribution of plastic material, so explosive origin, plastic material, tephra, most likely. And they try to reconstruct the source of this. After identifying this pyroclastic origin-looking tephra on the surface, they try to locate the source of this tephra, which has a lot of possible location. This is the list. Generally, from the Apollinaris Mons, the Tarsis Mons, Montes, the Arabia Terra, and Cerberus Fossa in Elysium, the Elysium planet. There are possible sources here where you can see on the map. So they try to identify locations. For example, the Apollinaris Patera was one of the possible proposed volcano or volcanic-like geomorphological feature on the surface of Mars, which was or which is one of the possible source of this tephra. They're still looking for it. So if you wanna do some research on Mars, you have a lot of source, and you don't even need a lot of money to do that, because most of the results are reachable, and you don't need anything else, just a good or relatively good computer with some GIS software, and you are like living in a geomorphological paradise if you visit the surface of Mars through the net. So another interesting found, and this is fresh, it's from 2000, this study is from 2021. So you can see what I was just talking about, that if you have a good eye, you can, good eye for geomorphology, then you can see a lot of amazing things on the surface of planets, especially, for example, Mars, because of the very high resolution pictures what you can get, and altimetry data, and different geochemical data from reflectance information. So they found a young one, some kind of geomorphological feature which may be some kind of active volcanism on the mark of active volcanism. It's close to the Cerberus Fossae, the Elysium Mons. It's not, let's say, not so far, not so far, it's around 400 kilometers from the Elysium Mons. Based on the crater counting, it's very young. It's, let's say, the oldest estimated age is 200,000 years. So it's in the geological history of Earth, it's the Ice Age, it's the Middle Pleistocene. So it's very, very young. volcanism, it seems that this region is seismically active, and but there are some evidence which tells that it might be some kind of fissure volcanism with some kind of material around this fissure, which is most likely a calcium pyroxene-rich material. They try to reconstruct geomorphologically. They try to add more geochemical information as well to support this idea, this fissure-fed pyroclastic deposit. It would be the pyroclastic deposit is around this fissure. They already found on the moon, on the surface of Moon and Mercury, they found very similar features, and it's also morphologically, morphologically, Mars morphologically, it looks very similar to this fissure-fed pyroclastic deposits. So there is a possibility that this volcanic activity is that Mars is still active volcanic. It still means that it was active in most likely 50,000 years ago. But these two are examples, was examples of the volcanism on Mars. Let's travel a little bit to the outer solar system. So when we passed Mars with Voyager, we reached the outer solar system. So when the gas giants are, when the gas giants, volcanism of gas giants, I cannot really talk about. We cannot have any information. We cannot really go through on the very, very thick atmosphere of gas giants. Is most likely that they have this surface or not. I don't think so. They have liquid hydrogen in their core, but around them there are different satellites. And if you focus on this one, this is a Io, the moon of Jupiter. You can see this change, this pulsating little spot here. And this is two photos. I merged these two photos into each other. Almost 1 year difference. This changing spot caught the attention of scientists because it means that the surface is changing on Jupiter. And then when Galileo arrived to Io, it discovered the most interesting and volcanically one of the most active surface in the solar system. So yeah, I wrote that it's really the home of volcano Hephaestus because the surface is continuously changing and filled with volcanoes. What are other evidences that this kind of plumes? See here, it's a giant volcanic eruption on the surface of Io. And although these are not animations, but you can see another one here, and another one here, and another one here. So after the different spacecraft arrived to Io, they were able to kind of reconstruct the change of the surface. That comes from New Horizon from 2007, and it reaches the surface of Io. And different type, they were able to separate different type of activity. I try to collect you here. Lava flows, active plumes, volcanic hotspot. So Io is a paradise in some sense for volcanologists. A little bit, if I were a volcanologist who interested in this type of volcanic activity, I would choose Venus or Io to do my research. But because generally you can see, so most likely Io has some kind of similar structure than the terrestrial planets. No, they got the core, or it got the core, deep mantle, asthenosphere, lithosphere. It doesn't seem that it has, of course, global tectonism, but these kind of plumes reaching the surface and creating this very, very versatile magmatism. It's a little bit terrestrial-ish. Not fully. It has a different trigger, but these, be expecting something like this to the, or these are the theories about the inner structure of Io. And an interesting parallel thing that this photo or this lithography, it's very similar to, in some sense, to this or that imagination or theory. This is an old, just to relax our mind a little bit, this is an old lithography about the Earth, how they imagine the Earth in the 17th or 18th century, maybe. Yeah, not so different from how we imagine, in some sense, how we imagine Io in 2022. So these terrestrial planetary bodies or planets and Io is kind of similar to each other. No, they have some kind of asthenosphere, magma oceans, but there are a big group of satellites or planetary bodies which, although have the differences in inner structure, it's built by ice, and this raised the question that okay, we can imagine that we have some molten rock, we can create magmatism. That for various reasons. If the trigger is the tidal heating, or the other trigger is the radioactive decay, it's easy to imagine, no, that we have something we have to rely on, and this is the volcanism on Earth. But what happens in the case when we have ice, or something like ice and mud slurry in some other planets? So that creates a very, very interesting feature in the solar system, and this is the cryovolcanism. This is the term which is somewhere in between or toward the way how mud volcanoes works in the surface of Earth, in some sense. And you will see it's slightly different because of material is different, or almost different. So most likely these planets, especially let's say Europa or these are mostly the moons of the gas giants. The tidal force creates this liquid water layer below the ice crust, and this liquid water or water-ish, like a mixture of water and different kind of rocks, creates this cryomagma which can surface, and that creates the cryovolcanism for us. The first and mostly, what can I say, target of the recent research is Europa, the moon of Jupiter. There is two missions which goes from NASA and some international collaboration which targets Europa, not only because of the geomorphological features on its surface, which kind of suggest that there is subduction, or how they call subsumption, on the surface of Europa, but the possibility of life in this moon triggers this research. So how the subduction idea came is it's nothing else, just the detailed research of the lineaments of on the surface of Europa. There's lot of different type of lineaments and their connection, which suggested that there are some missing part if they kind of reconstructed the connection of those lineaments. And it triggered the big argument, because some researchers said that the subduction is possible on the surface of Europa, but some model, of course, because we're talking about ice, so these are ice shells, that it's most likely it's a little bit different than subduction, but something like that. For sure, there are volcanoes on the surface of Europa. This is relatively one of my research target, or has been my research target for long, for even my university time. So it's a long love toward this moon, and some recent development in the and increasing the quality of the old Galileo images. It let me revisit and forced me to revisit Europa and look for cryogenic volcanism or cryogenic mud volcanoes. But you can see that's the lineament system that I was talking about. It's beautiful. It's so characteristic of Europa, and it tells a lot about the environment. It's similar. Some of them is similar for rift. Others are like fractures, like possibly related to kind of forearc or back arc basin, if the assumption does existing. And along the lineaments, you can find various features which are looking like volcanoes. I didn't. There is no name for these volcanoes. That's very, very fresh finding. So I can name them, but I just chose the name of the picture. This is the most characteristic, really cone-shaped like cryovolcano. You can see here. Even you can identify the cylindrical vent or the crater. The edge of the crater is intact, the crater rim, and it has really a cone shape, a nice cone shape. You will see that compared to other cryovolcanic or suspected cryovolcanic shape, the possible lack of the different kind of flow like lobes or features may suggest that these are some kind of vents for the water plumes, which recently was identified in some photo, and it's kind of cryo geysers or water eruptions. It's like an explosive eruption on the surface of Europa, and it creates some kind of water and ice mixture which explodes into the space. And of course, there are some material which builds the cone, but it's not effusive. There are no like cryo slurry lobes around it. Okay, but there are so let's see what's happening when there are some cryogenic material around the vent. So this is I named or identified it as a shield-like volcano. You can say that there are it's so-called chaos regions in Europa when it's like this, when you can see this kind of melting and freezing material in a mixture of chaos. it's maybe some surfacing material which appears because of the partial melting of the surface, maybe triggered by some heat, convective heat flow coming up from the deeper part of the moon. But among this, there were this feature here. If I do some magnification from it, you can see that it got a kind of rounded shape, which covers some kind of rounded shape feature, which covers the lineaments. It's sitting on the lineaments, so the lineaments can be the source of cryomagma. It sounds weird, but it's cryogenic cryo slurry. This subsurface material, this semi-liquid material from the deeper part of the moon, and it got some vent and let's say partially eroded crater rim. So compared to other chaotic or chaos regions, this relatively rounded shape and the center part, which I interpreted it as a crater rim, may be the evidence. So it's a geomorphological evidence, or can be a geomorphological evidence of a shield-like cryovolcano. And what happens if this cryovolcano just goes on and goes on and goes on and actively putting its material out to the surface of Europa? Now that causes a complex system. The history of this photo, that my first research in my entire life was related to the surface of Europa and mud volcanism and cryovolcanism in 2003. And this was the first picture which I used. I never or identified this feature as a volcano. I never, well, okay, I published it in an abstract. But it's a long history. So now I decided that I really do something with it. What you can see is some center with an eroded crater rim here. There are some line, and most likely the development of the lineaments is somehow connected to this volcanism. Some of the lobes of the cryo slurry is overlaps the lines. This is the most characteristic. Most likely this is the youngest one, and there are some older. This can be like, this is the youngest one. It's slightly older, and the oldest must be like this one here. Or it's still there is something here which might be even before that. I cannot see the connection. It's something like that. So what is interesting that it got its cylindrical vent, but you can see some fissure here, some lineaments. So it's some kind of cylindrical vent, but it got the fissure. So even the source of the cryo slurry can be these lineaments. So it's kind of let's say a cryogenic shield volcano. It's not really shield anymore, but some kind of volcano with this different generation of lobes. I think it's so beautiful that even the rhythm of the activity is identifiable in some sense in the case of this one. Okay, if you're interested in this kind of research on Europa, I can happily share things with you, because that's one of my field, my long-lasting love to this moon. So we left the gas giants. I'm sorry for Saturn and the ice giants, the Neptune and Uranus, because we just passed them. In 2015, New Horizon arrived to Pluto, which is considered as a dwarf planet. Unfortunately, it's not even a planet anymore, poor Pluto, and provided a lot of breathtaking, amazing photos from the surface of Pluto. It's so crazy, that some spacecraft can go so far where really the light of the sun is just like this dim light of a far star, and providing us these pictures. And of course, if you remember to our the first part of this presentation, you may remember that we were talking about that the elements at the close to the sun are very different compared to the elements of further from the sun, and now we are quite far from the sun. So on the surface of Pluto, what you have is not even water, some sense water-rich ice, but also you have nitrogen rich ice, and also you got some subsurface ocean, and it has this clatrate hydrite. Clatrate is generally kind of complex material. So you got even this layer which creates most likely, or you can suspect some cryovolcanic activity on the surface of Pluto. And yes, if you do so, you are not alone. There are scientists who already published their results and trying to how can I say, show the evidence for cryovolcanism. Yes, maybe. I would not argue with them because we don't have enough evidence that these are cryovolcanoes or not. But it's good that there is something where we can go, even if maybe these features are not cryovolcanic object. But why they think that these are ice volcanic or cryovolcanic construct? So the scientists call that there is three main line of evidence. One is an indirect one. There is only a few impact crater in the area. So it means that there must be some process on the surface of Pluto which renew the surface, which makes the crater disappear. So this is one evidence. They got this hammocky morphology, but it's not. It doesn't seem like anything like glacial erosion or some kind of erosion related to the volatiles which reaching the surface. So cryovolcanism seems to be a good explanation for those features. The important is the third part is that generally these features are elevated areas compared to the surroundings. So they are topographical heights, but it doesn't seem, doesn't seem that it's kind of erosional remnants. It seems that they just built above the surface. Okay, these are the sizes. The bright ones and the Picard ones are the names, and this is Pluto, and they in Pluto's poles, let's say, south pole. So these are the elevation data. Honestly, if I see this cross section going through the shape, this shape is kind of, I would say that, yeah, it's kind of possible from my sense, given the fact that you can see some craters, I mean volcanic crater type of feature, and unfortunately for me the elevation cross section is not that how can I say, I kind of expected some a little bit more like a crater shape in this case, but yeah, why not? And the other one is yes, that's also a little bit problematic from my sense, but let's say this crater kind of volcanic shape. Okay, if you want to read more about the this, there is one paper appeared in Nature Communication, and there is one in Science. I think. Wait, sorry. After all, I didn't put the third publication. There is one. It was published in a less. How can I say, less leading journal, and this one is a nice one. It's in the Journal of Volcanology and Geothermal Research. So if you search for Pluto and the Journal of Volcanology and Geothermal Research altogether, you will find it for sure. Yeah. Okay, so we left Pluto, and if we follow Voyager, then we now out of our solar system. So we're out of the bubble of the heliosphere of our sun, which means that now we the interstellar place, and we can start to look for exoplanets. So the planets which are not in our solar system, and they can orbit other stars, of course, or they can be these free floating exoplanets, which which can orbit the galactic center, which is a long travel for sure, and they can be rogue planets too. They just go through on everything. They are wandering around. They are the rebels. So we have. Honestly, I'm not definitely an exoplanet scientist, and I did not know that we already know more than 5,000 exoplanets, which is a lot, and there is a list of these exoplanets. So the question, they generally most likely made up of elements like the planets in our solar system. But how they mix these elements, it's maybe not like in the mixture of elements in our planets and planetary bodies which we just visited during our field trip. So there can be water and ice planets, iron and carbon dominated ones. So there are different ones. But how can we research them, or what can we do with them? So generally, the exoplanet size and masses they can measure, and from that you can estimate the composition. That it's most likely rocky or most likely gas-rich type of exoplanet. So like the gas giants or the terrestrial. If you can measure the energy radiated from by the stars of the planet, you can estimate the surface temperature on the planet. And these two information, it can tell a lot about what you expect, and from our sense that which planet may have a high volcanic activity or less, which planets are ocean type of planets most likely, or rocky planets. So from this data, you can get some basic information. Yeah, I wish, or I wonder when will be the time when we really can visit those planets. Yeah, interstellar travel is a dream. Yeah, so let's finish our long trip at the one solar system, which is one of the famous ones, is the TRAPPIST one, which is much smaller solar system than ours. You can see this is our solar system, and if you put TRAPPIST-1 in it, it's only this size. The TRAPPIST-1 is the name of the star, in the center of that solar system. It's an ultra cool red dwarf. So can you imagine that it's slightly larger than Jupiter? So it's surprising, but it contains 7 Earth-sized planets. So they're terrestrial type planets. It's a very crowded area around this red dwarf, and the habitable zone is only this. The E, F, and G are the ones which most likely I think that's similar to Earth in some sense. And this one is too far. These are too close to the star. Okay, so how their exoplanet look like it's difficult to know in this moment, but you can have some imagination about that how the volcanism happening if those planets have for example rocky surface, because it must be a little bit similar to the terrestrial volcanism like on Earth. But these are a lot of question marks, and it's not even a hypothesis. It's just almost like science fiction in some sense. Okay, so I think I finished a little bit earlier, but we did not have break. So thank you for your attention, and I hope you enjoyed this journey. And if you have any questions, just feel free to drop me some mail. I think I had my mail at the beginning of the presentation. Thank you.
Thank you, Balazs.
Thank
you
you
for this amazing lecture. I'm sure that a lot of the students got a lot out of it and must have eventually some question, even if they are a bit shy. I could see some of them, our other colleagues online, if they have any questions, anything they want to ask, it's the right time. And you can always ask later as well.
Yeah, absolutely. Please write me a mail. I will for sure answering.
Mahasiswa, kalau ada yang kamu mau tanya ya, bisa nanti mail dikirim Balazs Bradak. Karena di sini kalau sedikit apa ya malu-malu, tak apa-apa ya, nanti aja bisa kirim questionnya. Di email ya di PowerPoint, ada di PowerPoint. Nanti lihat PowerPoint, baca di PowerPoint aja. Okay, so I think we can end this session for today. Thank you very much. Much appreciated. And I will see you all sometimes maybe. And next week will be Aditya Saputra, and he will talk to you for the last lecture of this international series. Thank you.
Thank you.